Hello, welcome to Mystery Science. Today we're going to be looking at Newton's third law. So we're going to look at what Newton's third law actually says, and we're going to think about what equilibrium means and why it applies to forces. I'm also going to talk about action and reaction pairs and what that means in terms of Newton's third law and forces. And then we're going to have a look at collisions. And it's only going to be a brief look at collisions because there's going to be more about collisions in a later video. So the first thing we have to do is try and remember Newton's first two laws. If you can't remember Newton's first two laws, then here is a bit of help for you. I've got the laws written out with a couple of blanks. So pause the video and just try and fill in the blanks. Okay, welcome back. Well, remember that the first law is all about an object's motion. An object, for example, me. I am a science teacher. Let's think of me as an object. So Mr. E is currently motionless, and I'll stay motionless unless something moves me. So an object at rest stays at rest unless acted on by an external force. But also, if I was moving at a constant speed, then the same thing would apply. So Newton's first law says an object at rest or moving at a constant velocity, remember velocity, not speed, will remain like this until an external force acts upon it. And the second law is all about the force itself. And we can say that the force is proportional to both the mass and the acceleration. Remember, we did that experiment and we drew a graph and we proved that the force was proportional to the acceleration of an object, and the gradient of that line was the mass. So the acceleration of an object depends on the size of the force applied and the object's mass. And we can boil that down to a simple equation, and some people remember Newton's second law by this equation: force equals mass times acceleration. So our two laws are talking about the forces applied to an object. So at the moment, Mr. E is at rest, and he's staying at rest because there's no external force. As soon as there is an external force causing a resultant force, Mr. E will move. Ow! God, all right, calm down. All right, now then, those are the first two laws. So an object at rest stays at rest unless acted upon by an external force, or in constant motion unless acted upon an external force. And that force is equal to mass times acceleration. Okay, fine, that's easy. Now, what's Newton's third law? What else could this Isaac Newton have been going on about? Well, meet Bob. Bob is going to help explain Newton's third law. Now, I know that is a very photorealistic diagram, but don't be fooled. I drew that myself this afternoon. I know, right? So, Bob is leaning against the wall. Bob isn't moving. And quite importantly, Bob is not falling through the wall. The wall is there and not letting him fall through. But because Bob is leaning on the wall, Bob is exerting a force on the wall. Now, this is where it gets strange. Because there's no resultant motion, Bob is at rest. And Bob's staying at rest, but Bob's exerting a force. He should be moving, unless the forces are balanced. And this means there must be a force pushing back on him. So that force must be actually pushing back on Bob with exactly the same size force. But Mr. E, walls can't push. What are you talking about? Well, it's hard to think about this in terms of a wall, but you can think about this in terms of the floor as well. If you stood up right now, unless you're in some sort of cartoon and standing on a hole which you hadn't realized, and you suddenly look down, find yourself on a hole, and then fall through, that's not happening. You're standing on a floor, and that floor is pushing back on you. It has to be. Otherwise, you're falling through the floor. And we know this because of Newton's first law. Well, so is Newton's first law rubbish? No, it isn't. And I'm going to talk to you about how this works by talking about an interview that I once had. And a very esteemed gentleman who was conducting the interview said to me, all right, well, yeah, physics, it's the weirdest of the sciences, isn't it? Yeah, I get it. I understand that this chair, if I sit on the chair, there's an equal and opposite force to my weight pushing up, and so I'm not moving, and that's fine. But when I get up again, the chair doesn't change. It's still the same chair. Where did that force go? Where does it suddenly come from? It's not like the chair is sentient and all of a sudden it goes, oh no, buttocks must push back. Ah! No, it doesn't do that because it's an inanimate object. It doesn't have any knowledge. But chairs are made mostly of springs and cushions and things with springy bits inside or foam that pushes back. Now, let's think for a minute about chairs at school. If you sit on those lovely plastic chairs with which we provide you, or indeed a wooden stool or a plastic stool, or who knows what you have at your school. But at my school, we have plastic chairs. When you sit on the plastic chairs, let's say the chairs are flat, and I know they're not, I know they're curved slightly, but when you sit on them, they deform slightly. That plastic is able to bend, and you don't feel it because it's not that big, but you can see this happen. If you watch an adult sit on one of those chairs, you can actually see the plastic at the sides raise slightly. Now that bending, that changing of shape, if you think about all the atoms inside the plastic all lined up, when they're sat on, they're bent, and this pushes some atoms closer together and pulls some atoms further apart. All of those forces are then trying to get that back to normal. It doesn't like being stretched, so it tries to bend back. And in doing this, it's forcing back upwards on you. And so when you stand up, it goes back to its normal self. So this force is pushing back up on you. Now that's easy to think about. These are springy. But what about the floor and this wall? Well, they're springy as well, kind of. Now I know that a brick wall is very, very, very sturdy and is definitely not springy. But if you push on it, there is enough of a tiny, tiny deformation. Remember, its mass is involved as well, and the wall is very heavy. It's much heavier than Bob. Therefore, it doesn't need as much of a movement to push back. And so that's what's happening. The same with the floor, the same with the earth. Now, when you jump in the air, we know gravity pulls you back down. These forces aren't just contact forces. So if I suddenly leap into the air, then there has to be an equal and opposite force. But we know those forces aren't balanced because I'm going to accelerate. I'm going to come back down. But the Earth does move slightly, and I do mean slightly, so slightly that it's actually completely imperceptible in much as it doesn't really move at all. But it does actually rise up to meet you a tiny bit. And if you got everyone on the whole planet, this is a question I always get asked when I bring this up, if you were everyone on the whole planet, all 7 billion people, and stood them side by side, you'd probably get actually all of them onto the area of the size of the Isle of Wight, which is also mind-boggling. But you got them all to jump at the same time and then come back down. The Earth would move, but again, such a tiny, tiny amount, because even 7 billion people, their mass combined is nothing in comparison to the mass of the Earth. So whilst the Earth does move, it's only a tiny, tiny amount, and it wouldn't even cause a wobble in its orbit. Okay, so we can't propel the Earth onto a different orbital path by jumping up and down, which is lucky, actually, because it'd be really terrible if we could. So Newton's third law comes down to this. For every force in one direction, there's an equal and opposite force in the opposite direction. Now, we call these action forces and reaction forces. If I push on a wall, the wall pushes back, it reacts. Okay? And because it's so much more massive than I am, then I can't feel it, I can't see it. It's completely imperceptible, but it is there. If I put my hand on a spring and push, then the spring is definitely pushing back. There's an action and a reaction. All right, now it's over to you. I want you to write down a full explanation about Newton's third law. What is it? To give you a hand, here are some keywords below. If you're not quite sure, rewind the video, go back to my explanation and see if it makes more sense with these words in mind. And I'll go through a model answer in just a second. So pause the video, have a go at that, go back if you need to. Okay, so remember your keywords. The pair of forces acting upon an object are often called action-reaction forces. So whenever I have an action, for example, me standing on the floor, there is a reaction force, a force that pushes back in the opposite direction. Now, there's no acceleration in these examples. Therefore, the forces are balanced. So the two forces are always the same size and acting in opposite directions. For every action, there is an equal and opposite reaction. So have a look at your answer, see how it compares with that model answer. Okay, let's look at an example. Here we have a dog. The dog is pulling on a rope, some sort of pulley toy thing, and these are the forces on the dog. So remember that these action-reaction pairs of forces act on two different objects. So we have two different situations here. This dog is standing on the ground. So the weight of the dog is pushing on the ground. The force from the dog on the ground. Now, the ground has a reaction force and pushes back up on the doggo. The force from the ground on the dog is an equal but opposite force. So it's the same size, equal but opposite direction. Okay, so its force of the weight has an equal and opposite reaction force pointing upwards. And they're in equilibrium. Nothing is moving. The forces are the same size. Now, same with the rope. The dog is pulling on the rope is pulling on the dog. Okay? So the force from the rope on the dog is opposite to the force from the dog on the rope. Okay? So for every action, there's an equal and opposite reaction. Newton's third law. Simple. However, when we think about one object, for example, the dog, we think about all of the balanced forces on the dog. Action-reaction forces involve two objects. So in the previous picture, we have the dog, the weight of the dog pushing down on the floor pushing up on the dog. Two different objects. The dog was pulling on the rope was pulling on the dog. So you had two different objects. We had the dog, the rope, we had the dog, the floor. Two different objects all the time. When we go back to Newton's first law, we have to think about balanced forces on one object. The dog isn't accelerating in any direction because all of the forces on it are balanced. Now we have to change the language slightly to think about this. So the force of the ground on the dog is pointing upwards. The force of gravity on the dog is pulling it downwards. Okay, so both of those are about the dog. The force of rope on the dog and the force of friction on the dog. Okay, so the force of friction is pushing in the opposite direction. I shouldn't say that because I'm the other way. But the force of friction is pointing this way on the dog. So these forces were on the dog. Now this is probably the hardest concept of Newton's third law, is the two different examples. When we're talking about action-reaction forces, we're talking about the forces of one object on another, and then the reaction forces on the second object back on the first one. So we had the dog and the floor. Now, when we're looking at balance forces, all of the forces are about the dog. The force of ground on the dog, the force of gravity on the dog, the force from rope on the dog, the force of friction on the dog. Everything's on the dog. Okay? So action-reaction forces, two different objects. Balance forces, the same object. Okay? And that's a difficult concept. So what I'd like you to do is stop the video, go back a little bit to the beginning of the last explanation, play that through again and see if you can get it. If not, feel free to send me a comment and I will try and explain it slightly differently. Right, here you go. Here is a thing to do. For each of the following, state what the other force in the action-reaction pair is. So, first one, I have a student exerting a force on a book as he picks it up. What's the reaction force? Number two, the Earth exerting a force on the moon. What is its reaction force? Number three, a monkey exerting a force on a branch as he hangs from it. I am quite aware that that is a picture of a rope and not a branch. Sorry. And number four, the force a horse exerts on the floor as it gallops along. Okay, so in example one, the student is exerting a force on the book as he picks it up. The book is exerting a force on the student because the weight of the book is acting in the opposite direction. The student has to do work to move the book. He has to apply a force in the opposite direction to the weight of the book. So the book is exerting a force on the student. Now the Earth and the Moon is similar to the one that I was talking about with all of the people jumping. The Moon is a large object and it exerts a force on the Earth. But the Earth is the bigger one, so the Moon orbits around the Earth. And it orbits around the Earth because of gravity. The Earth pulls the Moon towards it. But because they're both objects, there's an equal and opposite force in the opposite direction. The Earth also moves towards the Moon, but because the Earth is more massive, the acceleration is much smaller, so it just doesn't move as much. Number three, the monkey exerting a force on a branch as he hangs from it. Well, the branch pulls the monkey back up again. So the monkey is pulling down on the branch pulls up on the monkey. And the same as the horse on the floor. We've talked about things with the floor before. The floor is pushing back up on the horse as it gallops along. There's friction force that is stopping it from slipping all over the place. And remember always that action-reaction forces act upon different objects. You have to use both objects in the language that you use. Okay, cast your mind back to my amazing photorealistic drawing of Bob, and I'd like you to do a similar drawing, probably not as good as mine, obviously, but draw a sketch, or a stick man if you have to, of someone leaning on a wall. Now I want you to add arrows to show the action-reaction pairs of forces, both in the vertical, that's up and down, and horizontal, that's left and right. Now, also, once you've done that, I'd like you to try and describe the action-reaction forces when you're sitting on a chair. Now, if you don't know either of these, and you can't figure them out, then again, go back a little bit and have another listen, because I go through both of these examples. All right then, let's move on to collisions. We've learnt about action-reaction forces. If I prod something, then it reacts back. There's a force pushing back on my finger. Now, this is good, and we know about these and kind of almost static situations and moving. But what if I throw a football at your head? Or if somebody throws a football at my head and football comes along, here it comes, and then it hits my head, what's going to happen? Well, I have a collision. So the force of the ball hitting my head is going to have an equal and opposite reaction force on the ball. Now, the mass of the two objects are very different. The mass of the ball is very much less than the mass of me. So the effect of the force, even though the force is still the same size, the effect of the force is very different. Remember, if you apply a force to me, my mass is roughly 100 kilograms. If you kick a football at me, which weighs, I don't know, let's say a kilogram, it probably doesn't weigh that. In fact, that's just crazy. But let's just, for the sake of argument, say the ball weighs a kilogram, and the kilogram ball hits me in the head. Now, actually, if a kilogram hits me in the head, that's going to hurt. And yeah, it's going to hurt, but it's not going to accelerate my body mass much. There's going to be an action force, but then there's going to be a reaction force. Now, I have to move, and so does the ball. But the ball is going to accelerate much more. And people use this to their advantage when they play the football. Here we go. Here is a famous football man with his head attached to a ball. Now, obviously, in this picture, the football has hit famous football man in the head. Famous football man is therefore, I believe the term is heading the ball towards something net-shaped. So he's using the collision to his advantage, and obviously I'm being silly, but no, football really isn't my sport. But could you please try and state the action-reaction forces that are present here? And then describe the effects on the two objects and explain why they're different. Okay, so the ball is exerting an action onto, I'm going to say that this is Cristiano Ronaldo's head. So the ball is hitting this guy in the head, and that man is then heading it back again. Now he's applying an extra force. He's going to flick it expertly and deftly towards the goal, probably. But there's a reaction force. So even if this was a still image and he had absolutely no idea this ball was coming, the ball is going to come and it's going to hit him. That's the action force. The reaction force is then the force from the guy's head onto the ball. Okay? And he looks very upset about this, probably because his hair is now slightly out of place. You know how these, superstar footballers are. So the effects of the object are going to be vastly different because Cristiano Ronaldo is a well-built, tall gentleman, and that ball is very much less massive. So the same force is going to be applied onto Cristiano Ronaldo's head. I mean, this is why it stings when a ball hits you. And then the same force is going to be applied back to the ball. But the ball is going to move much more rapidly than Cristiano Ronaldo. I mean, his head might snap back a little bit on the collision, but really not much because it's much more massive than the ball. The ball has a lower mass. Now, Newton's second law says the force is equal to mass times acceleration. You have a low mass here and a high force. You must have a high acceleration. And so the opposite is true for the footballer. If you have a large mass and the same force, then you have a smaller acceleration. In fact, it's almost imperceptible. He doesn't move very much at all. So much so that actually he's probably flicking that ball back. And they're going to score, I don't know, some points or something. And everyone's going to cheer and run around and throw their shirts over their heads. And all of the people in the stands are going to go crazy, except for the ones on the other team who are going to be very sad. And some cheering and football will be won. Okay, so here are your final questions. Please make sure that you know the answers to these before you end the video and move on. If you don't know the answers to these, go back a little bit. So the first thing I'd like you to do is explain Newton's third law in a sentence. So that's not just state it. Anyone can do that. I want you to try and explain what it is, but just in a small sentence, maybe a couple of sentences. What are forces in equilibrium? What is equilibrium and what does that mean? How are action-reaction pairs different to balanced forces? Now that's going to be the tricky one, I think. Now, and give an example of an action-reaction pair of forces. That should be easy because I've given you a bunch of those. So I'm going to leave you with those questions then. I want you to make sure that you know the answers to those, and then join me for the next video, which is going to be more about momentum, which is going to be pretty awesome. Right, I'd like you all to stay safe, please, and I will see you soon.